Hello and welcome back to Chapter 8, Section 2. We are going to find the area between curves that are not always the vertical kind. So, what happens is sometimes when our functions are a little different, we might not always want to draw vertical rectangles to find the area between them. So, the area between these curves is obviously not going to be well defined by a vertical rectangle. So, as you look at these problems, we maybe could figure this one out, but there's these points where they intersect. I'm not sure where they are, and we might have to break that up. Anyway, that would be really challenging. So it's much easier if you turn your head, tip your head to the right, so that this is your positive upward axis, and then you can look at this vertically, it's horizontally with respect to y. So in order to do that, the only thing that really needs to happen is your function needs to have y as the variable instead of x. So you need to have x equals a bunch of stuff with y instead of y equals a bunch of stuff with x. Then we can do the integral just like we did before. The integral over the interval of f of y minus g of y dy, whichever one's on top. Remember, you tip your head to the right, so this is the positive x-axis. So in this example, the f of y would be the top one, and the g of y would be the bottom one. So it's basically right minus left. That's another way to think of it. All right, so let's do an example here. We want to find the area of the region bounded by the curve x equals y squared minus 1 and y equals x plus 1. So I'm going to start out with just sketching that so I kind of know what it looks like and which one's on top, because it's important to know so that we get it the right direction. Also, we're finding an area, so it's positive. So if you subtract and you get a negative, then it's probably you just did them in the wrong order. So let's graph. X equals y squared minus 1 is a parabola that's sideways. And this shift, because it's in the y direction, is to the left one. So it's a parabola that's been shifted to the left one. I'm going to make my scale really big so we can see what's happening here. So that's -1. And then this is +1. And this is -1. So when I draw my parabola sideways, it's going to go like this. And then the line, this one is y equals x plus 1. So it's in our normal y equals format. We're going to have to fix that in a little bit, but it goes through 1 with a slope of 1. So here's my 1. And that means it would go through -1 and go up here. So there is my line. Now what it asks for is the area of the region bounded by the curve. So that would be this area that's in between the two. It's a little tiny sliver, so we should get a pretty small answer. This box is only 1 by 1, so it's definitely going to be a little fraction that we find here. Now, I could do this with respect to x, because I could do the parabola minus the line and do little vertical rectangles here, and that would be acceptable. We can do it both ways. I'm not going to do that because if I wanted to solve this, I would end up with the square root of x, and that's just not as clean to find the integral of, or the antiderivative of. I'd rather leave it as y squared and change this equation by subtracting 1 from both sides. I get x equals y minus 1. That's the same equation, just solved for the other variable. And now they're both respect to y. So now turn your head sideways here and take a look at this graph. And I could do horizontal rectangles and then do the integral of that. So if we turn it sideways, our integral with respect to y, so you need to use y interval here. So we're going from, if I look at the y-axis, this is 1 and 0, from 0 to 1 of, and the one that's on top is the line minus the one on the right, right minus left. So the line goes first, and my line, I rearranged. My line is y minus 1 minus the other function, which is y squared minus 1 dy. Make sure you use the proper variable here, and proper notation. So if we evaluate that with respect to y, I didn't take the time to find these 0 and 1, but you could set these two equations equal to each other and solve them. I could tell from my graph that they cross at -1 here, 1 here, and 0. So let's go ahead and evaluate this integral. So I should clean it up. What is that when we subtract? So we're going to have negative y squared plus y, and then my ones cancel, so dy. The antiderivative of negative y squared is negative y cubed over 3, negative 1/3 y cubed, plus the antiderivative of y is 1/2 y squared, or y squared over 2. We're going to evaluate that from 0 to 1. So when you plug in a 1, you get negative 1/3. When you plug in plus 1/2. And when you plug in a 0, you get 0. So we just have to do negative 1/3 plus 1/2. You can get a common denominator and turn those into fractions, but 1/2 minus 1/3 is 1/6. So the area of this little curved piece is 1/6. Let's try another example. Okay, for our next example, we're going to find the area in quadrant 1 between the x-axis and y equals x minus 2 and y equals the square root of x. I'll start again with a little drawing so that we know what we're looking at. So first of all, we have the line. Let's do the square root first. The square root of x starts at 0, 0, goes through 1, 1, and the square root of 4 is 2. So I'm going to graph that curve, square root of x. The other line is a line y equals x minus 2, so I start at negative 2, and the slope is 1. So there's my line. Now I want to find the area of that curve in quadrant 1, so above the x-axis, below the square root, and to the left of the line. So I'm looking for this curvy little shape right here. Now there's 3 ways to do this problem, and I'm going to show you all 3 ways, but I want to talk through them a little bit first. So what we're used to doing is integrating with respect to x, so we can do this vertically, and we're actually going to do that first. If we do it vertically, we get little rectangles right here, and they start at the square root of x, and they go down to the x-axis. We don't want to go just subtract the 2, because then we would get this area here, and that's not what they asked for. They said between the x-axis, the line, and the curve. So when I get to this spot right here, I'm going to have to change my plan, and I'm going to have to integrate between the 2. Right here, it's just under the square root of x to 0, and over here, it's between the 2. So I'm going to have 2 separate integrals. If I turn my head sideways and do it with respect to y, that's method 2, and then method 3, I've just got a little geometry piece in there that we'll throw in. So however you look at the problem, you can choose to do it. We're going to start with integrating this with respect to x. So what I explained there is we're going to have to do it in 2 pieces. First of all, let's go the integral from 0 to 2, and we just have to do the square root of x, because that's all we want up to the x-axis. Then we're going to add this other chunk that's over here, and that one is the integral from 2 to 4, because the place where they intersect there is 4. And we have the square root of x on top minus the line, which make sure you put parentheses around x minus 2 so you don't mess up your negative signs. Don't forget your dx. And then we've got the proper notation here, and we're going to go ahead and evaluate those integrals. If you want to try it on your own, pause the video and come back and see if you get it right. You can fast forward a little bit. All right, so the antiderivative of square root of x, I think about that as x to the 1/2. So the antiderivative, we would need to have 2/3 x to the 3/2 evaluated from 2 to 0. Oops, no interval sign on that one. And then we need to do that again here. So the antiderivative of square root of x we just did is 2/3 x to the 3/2. This is negative x, so minus x squared over 2. And then don't forget this minus negative is actually plus 2. So the antiderivative of positive 2 is 2x. We're going to take all of that from 2 to 4, and we're going to compute those. So probably the fastest way is to type that in a calculator. If you don't have a calculator, you're going to plug in these numbers and figure them out. Answer, this comes out to this plus this is 3 1/3. All right, now we're going to try the other two methods. All right, now we're ready for method number 2. So instead of looking at this in terms of x, we are going to integrate with respect to y, just like the example that this part of the lesson is on. So instead of trying to look at it vertically and breaking it into 2 separate parts, we can turn sideways and look at it like rectangles like this. That would be a lot easier because we only have to do one step. So we're just going to go ahead and start the integral. Now in the terms of y, how wide is my interval? It goes from 0 to 2. The height of this is 2. So when I look at the y-axis, we're going to go from 0 to 2. And then which one is on top or which one is on the right? So if you turn your head sideways or just think about right minus left, we have to do the line first minus the curve. Now, in order to do this, we have to have our equations in terms of y. So you can't write the equation with an x if it's in terms of y. So in order to do that, we got to solve these. So this one, I would add 2 to both sides. So I have, that's the line which is going to go first. I have x equals y plus 2. And on this one, I would square both sides. So x equals y squared. Oops, that's not an equals. That's a minus y squared dy. Now, I probably should put another set of parentheses around that. Okay, so I need to evaluate that. Let's clean it up a little bit. So I like them to be in order. So negative y squared plus y plus 2 dy from 0 to 2. Okay, antiderivatives. You can go ahead and solve this problem without me. If you want to, pause it and I'll write out what I got. So the antiderivative of negative y squared is negative 1/3 y cubed, or y cubed over 3, plus y squared over 2, 1/2 y squared, plus 2y, and we're going to evaluate that from 2 to 0. I forgot the line. If you plug in a 2 to each of these, you will get 3 1/3, just like the last problem. Minus 0, if you plug in a 0, you're going to get 0. So answer same as last time. Probably a little smoother because we only had to evaluate the integral. There were no square roots here or anything. Now let's take a look at the third option. So for method number 3, we're just going to kind of look at this a little differently. I could still evaluate it with terms of x. I also see a triangle in this problem. So another way to do this would be to find the total area under the square root and then just subtract off that triangle. So it would be the integral from 0 to 4 of the square root of x dx. So one-step thing. And then I just need to minus this. This is just a triangle, 1/2 base times height. The base is 2 and the height is 2. So that's just an area there. So area integral minus the area of that little triangle. If you do that, the antiderivative of this one is 2/3 x to the 3/2 because we have 1/2 there. Evaluate that from 4 to 0 minus 2. So that would be 5 1/3 minus 2 is 3 1/3. All 3 ways got the same answer. So there isn't a wrong way. Well, there is, I'm sure, but any of these 3 ways will still get you the right answer. You pick what works for your brain, but practice the integrating with respect to y. Sometimes that's the only way you can do it. Sometimes you have options like this problem. So go ahead and do your 8-2 assignment and post any questions on Google Classroom.